Hey everyone. So in this video, I'm going to go through a sketch of the proof of the existence uniqueness theorem for 1D continuous dynamical systems. Now, I'm not going to go through the entire proof in all its details. For that, I can point you to the packets I handed out. The full proof is written there. But instead, what this video is going to focus on is sort of three parts. So the first part, I'm going to go over an overview of sort of the main ideas of the proof, sort of like what the proof is doing to prove this theorem. And the key idea there is I'm going to introduce something called Picard iterations and what those are. Second, I'll do a motivating example showing how Picard iterations work in practice. And third, I'll present sort of like one key idea which is used in the proof. And so that's sort of the broad sketch of what the video will be. Again, for more details, I'll point to the packets or come talk to me for more. So let's start. So let's suppose we are given some dynamical system, some first order ODE, x dot equals f of x, and we have some initial condition x of 0 equals x naught. Okay. And so the goal is, how do we prove that there is a solution? How do we prove the solution is unique? And the idea here is that we know nothing about f except, right, the hypotheses of the theorem are that f's continuous, f prime's continuous. But, I can't use partial fraction decomposition. I can't use separation of variables. I mean, I know nothing about f, right, necessarily. So I need a proof technique that's going to be sort of robust for any possible f. And so what's the key? Well, step one of the sort of proof idea is to actually transform the differential equation x dot equals f of x into another form. And so what we're going to do is integrate both sides from 0 to t. And so what I'm going to do is say, well, this is x dot, and because I'm using t as my integration bound, I'm going to integrate with respect to, let's call it s. So x of s ds, and I'm going to integrate the right-hand side from 0 to t again. Here, f of, so x again is the function. So just to be explicit, right, x depends on the time s, and then ds. Okay. I'm doing this, right, to make it very clear that when I'm integrating, I'm actually, f itself doesn't depend on time, but the function inside of it does depend on time. Okay. Well, on the left-hand side, well, I can say something here, right? I have the integral of a derivative. And so by the fundamental theorem of calculus, I can integrate this. The antiderivative is just x, of course. And so I get x of t, the upper bound, minus x of 0, the lower bound, equals the right-hand side. Yeah, we're sort of stuck here. So integral 0 to t, f of x of s ds. Now, fortunately, x of 0, I do know what that is, right? That is my initial condition. So that is the value x naught, which was given to me at the beginning of the problem. So I can rewrite all of this. If I move that to the right-hand side, I can say x of t equals x naught plus the integral from 0 to t of f of x of s ds. Okay. So be very careful here. In some sense, it looks like I've solved my equation because I have x of t on the left-hand side and have a formula for x of t. But it's a little more subtle than that, right? Because I have x of t here, but of course, x is also in the right-hand side. So in some sense, this is still an equation with the unknown function x. And to solve this equation means to find the unknown function x that, when plugged in, solves the equation completely for all t. But this is still useful to do. Sometimes we call this final equation the integral equation. And in fact, because all the steps I did this way can be reversed back up this way, we know that in fact all of the solutions of the first equation, the original differential equation, are also solutions of the integral equation and vice versa. So it's just another way of writing down the same set of solutions. And in some theoretical applications, like what we're going to be doing today, this integral form is actually much more handy for us. Okay. Okay, so the goal now is, okay, how do I solve this equation? So how do I find the x that could plug into this equation? Well, let's talk about it. The idea is, I don't necessarily know what function x plugs in, but what I could do instead is try to do a simpler thing, which is, let's start with a first approximation, a first guess, call it x1, which probably isn't a solution. But then what I could do is try to use that x1 to give myself an x2, which maybe is not a solution still, but is closer. and then x3 and x4 and so on. And so I have a bunch of different functions, which in the limit would converge to the correct function, x infinity. So that's the goal, right? X infinity would actually be the solution. What does this look like? Well, it turns out there's a really clever way of doing this. So for x1, my first function that I would guess as the solution to my ODE, well, I don't have much to go off of. So the typical thing to do is just assume it's the constant function x naught. In other words, take the first guess to be just a constant function, which is the initial condition. Almost certainly is not the right solution, right? But that's fine. What do I do from there? Well, I'll define x2 to be x naught plus the integral from 0 to t f of x1 of s ds. Now, what have I done here? Notice that this equation I've written down looks very much like the integral equation from the last page, but importantly, the difference is on the right-hand side, I'm plugging in the x1 function, which is known. So in fact, the entire right-hand side of this is all known. So I can compute the right-hand side. I could, theoretically plug everything in, solve, and then that would give me an expression for x2. And so this gives me a formula for x2, which is completely, well-defined. It's possible to just calculate this and say what it is. Okay. And so in general, I sort of do this inductively. I could say, in general, xn would be x naught plus the integral from 0 to t f of, and I'm going to plug in the xn minus 1 function approximation into that integral. Okay. So this, we've just written down, we could do this over and over and over again, right? So I can plug in x2 on the right-hand side. That'll give me an x3 formula. Plug x3 back into the integral side, and then, I get an x4. And do this over and over again for every n. So if I do this for all n, the hope is, right, that although xn, each xn individually is not a solution necessarily to the equation, to the integral equation, in the limit, sort of, if you just imagine taking n to infinity, on the left-hand side, you get x infinity equals x naught plus integral 0 to t f of x infinity. Again, I'm taking like the n minus 1, also taking the limit as n goes to infinity. And so if this sort of limit makes sense, if this happens the right way, then what I end up with is this x infinity, which actually is truly a solution to the integral equation, right? Because if you think about the integral equation on the last slide, it was exactly this equation, right? And importantly, now the same function is on the left and the right. So it truly does work, okay? And so this idea, right, of sort of building xn from the previous step and then just doing this inductively, this is what's called a Picard iteration. Okay. And so the idea of the existence uniqueness proof is to, one, sort of just say that this proof works, or so that this idea works. So if this iteration procedure works, then I will have proved that there is a solution, right? If I can prove that there is a limiting function x infinity, that is a solution, right? So that proves existence of solutions. Of course, one could argue, well, what if I started from a different x1? What would happen then? Well, it turns out you can also prove that no matter what you choose as x1, it always converges to the same x infinity. So in particular, this proves uniqueness, okay? Because the x infinity we got here is a solution to the ODE. And in fact, no matter where you started in this Picard iteration procedure, no matter what you started from, it always converges to the same thing. And so that thing it converges to is the only possible solution to the ODE. So this is sort of the key idea, this Picard iterations. So because this is so fundamental, so this is sort of the overview of the proof. What I wanted to do is actually a motivating example, sort of showing you what Picard iterations look like for a specific ODE. So let's do that next. Okay, so we're going to illustrate this procedure, this Picard iterations for f of x equals x. So in other words, this ODE where x dot equals x, and I'm going to give you an initial condition x of 0 equals 1. All right, let's go ahead and start. The Picard iteration says, okay, first start with x1 of t to be 1. Okay, because y is just the initial condition. So what is this function? If you just plotted this, right, it'd be the function, which is just constantly 1 for all time. It does, of course, pass through the initial condition 0.01, but that's about all it does, right? Certainly, this does not solve the ODE, but fine. Let's write down our Picard iterates really quickly, right? Just from the last slide. So xn, remember, is x naught plus the integral from 0 to t of f of xn minus 1 of s ds. And now for this particular problem, because my function f of x is just the identity function, it's just x itself. So for this problem, we can actually write down the Picard iterates are integrate from 0 to t, and then I'm plugging in not f of x, but I mean, it is just x itself, right? It's the identity function. So this is what the Picard iterates will look like here. So let's go ahead and plug in this formula to calculate x2 of t. Well, by definition, it's supposed to be x naught plus the integral from 0 to t of x1 of s ds. And so x naught is 1 plus the integral from 0 to t of, so x1, what is x1? That is just the function 1. So I'm going to plug that in, 1 ds. And I can integrate that, right? So the integral of, so the antiderivative of 1 is s, and I'm integrating from 0 to t. And so I get 1 plus, so I plug in t, I get t minus 0, so 1 plus t. Okay, so that's my x2 function. So x1 was 1, x2 is 1 plus t. And again, you could think about plotting this and asking yourself, is this a solution to the ODE that I've given you? And the answer is probably not. Yes, I mean, it still fortunately does go through the right initial point, 0, 1. But yeah, it does not seem to satisfy the ODE. Okay, but maybe it's better. It's not just a constant. It's at least a line this time with some slope. Okay, let's keep going. So x3, right, again, will be by definition x naught plus the integral from 0 to t of x2 of s ds. And so that's 1 plus the integral from 0 to t. And now x2, right, what was x2? It's 1 plus t. So I'm going to write it with s, right? So it's 1 plus s. And so when I integrate 1 plus s ds in here, what I'm going to get is, okay, the antiderivative is s plus s squared over 2 evaluated from 0 to t. Okay, so what do I get? 1 plus, when I plug in t, I get t plus t squared over 2, and then again, minus some zeros, which I don't need to think about. Okay, so that's my x3. And so you see that what's kind of interesting about this Picard iterates, right, is every time I sort of take the next iterate, I'm going to get, in this case, like a parabola. But every time I do this, I get like a slightly more complicated looking function, which in some sense, let's say, is getting closer and closer to the correct function. So maybe you can convince yourself that if I plugged in x4, or you can check for yourself, right? When I plug x3 into the integral and evaluate, you're going to end up getting 1 plus t squared over 2 plus t cubed over 6. And then at that point, maybe you start seeing a pattern. And in fact, you can convince yourself in general that the nth approximation here is going to be a sum from n equal, sorry, let me not use n, let me call it maybe I, from 0 up to n minus 1 of t to the ith power over I factorial. And that maybe looks familiar, doesn't it? Right? So if this is true for all n, and we want to maybe think about what happens as n goes to infinity, well, this does have a well-defined limit. In fact, we recognize this is really just the Taylor series. This is the Taylor series of a very familiar function. So as n goes to infinity, this would converge to this infinite sum from I equals 0 to infinity now, t to the I over I factorial. And yeah, that is none other than the exponential function, e to the t. And if I went back to the original ODE and said, well, what's the solution to this ODE? You do know, and hopefully could check that the solution is exactly e to the t. This is like one of the classic separable ODEs you can solve. And so what's really cool about this is that we discovered e to the t by just doing this limiting procedure, right? So at every moment, x1, x2, x3, xn, none of those were solutions to the ODE, but in the limit, it converged to the correct solution to the ODE. That's the power of these Picard iterates. Okay. So the claim is basically that no matter what f you gave me, this procedure would work, okay? And so how does that actually work? Well, the idea is, so I'm not going to go through the whole proof, but the key is something called a contraction mapping. And so let me just sort of in the last bit of this video say a little bit about what that is. So first, a little bit of notation. So suppose I gave you two functions, x and y, which maybe I plotted here on the on this plane. And so the uniform metric or the uniform norm is a way to measure the distance between these functions. And so it has this notation. So I'll write double bars around them and a little subscript infinity. And so x minus y with these double bars, this metric or this distance between them is defined in the following way. It's the maximum for all possible t's of the absolute value of x of t minus y of t. So what does this mean? Well, it's easy to understand graphically. So what does this mean? Well, it means consider a bunch of different t's and ask what is the vertical distance between x of t and y of t. So, sorry about that. So as I start over here and ask again, what is that vertical distance, right? For this t value, what's the distance between x and y? That's like some length. And then as I consider different t values, you see that the vertical distance between these two functions, right, it grows and shrinks, and it might be zero, right? Sometimes if they intersect, it'll be zero distance, right? But the question here, the uniform norm or the uniform metric is the maximal possible distance between these two pictures. And so I've marked it here for these two functions. There's some specific moment, some particular t, where this distance is maximized. The length of that distance or the length of that line that I've drawn, that is the uniform distance or the uniform norm. Okay? So in particular, maybe something to sort of check comprehension, if the uniform norm is zero, so if the distance between them is zero, well, what does that mean? That means that there's never, so for all t, right, the distance is always zero, so there's never any space between the graphs. And when does that happen? Well, that must be the case precisely when they're the same function, right? So x and y must be the same function for all t. So in other words, this idea of uniform metric or uniform norm, it's a way of testing whether or not two functions are the same. That's one of the applications of it. Okay. But more generally, it's a way of saying how far apart are two functions. Okay. And so the last thing I'll sort of mention is that the key to proving the theorem in generality is using something called the Banach Fixed Point Theorem. Now, this is a theorem that arises in topology, it arises in analysis, and so the version I've written here is sort of tailored for specifically our class, but there's sort of much more general formulations of this that you can find in other textbooks. So what does it say? Well, it says, okay, let x be C1, which if you remember, it's the set of all functions f and f prime, both continuous. And suppose f, this capital F, is an operator, that's a contraction. And so what does that mean? What's an operator that's a contraction? Well, so when I say operator, I just mean something that takes in one function from C1 and spits out a different function from C1, okay? So as an example of an operator you already know, the derivative is an operator, right? I start with the function, I take its derivative, it transforms it into a new function. And so f is any such operator that starts with functions, ends with functions. And so what does it mean to be a contraction? A contraction means that this very special inequality is satisfied. And what does this inequality say? It says, if I take any two functions, phi and psi, and I measure the distance between them, so I look at how far apart they are, and then I apply that operation, that capital F operation, to both of them and ask how far that distance is, it's always shrinking. No matter which 2 points you gave me, which two functions you gave me, before and after transformation, they have all gotten closer together. Okay, this lambda is some number between 0 and strictly less than 1, right? So this is in some sense like the contraction ratio, right? It's telling us, how much things shrink by. Okay. And so, for example, if lambda equals a half, that's saying that, if two functions were 10 apart at the beginning, like there's a max distance of 10, then after you transform them by this capital F operator, the distance is at most 5 between them. Okay. And so the power of contraction mappings is, well, if you start with any function to start, x1 is any function, remember that capital X is the space of C1, then the sequence xn, defined as f of xn minus 1, necessarily, always, always, always converges to the same limiting function x infinity. And in fact, that x infinity is the unique fixed point of that operator. Okay. So what does this have to do with our problem? What does it have to do with Picard iterates? Well, let me translate a bunch of this to our setting. So for us, f of phi is the Picard iteration map. In other words, you take your initial condition plus integral of 0 to t of f of whatever that phi you're trying to, plug in is. That's it. For us, this is our operator, right? We start by plugging in whatever function you want into that integral side, and then when you evaluate, it gives you a new function back out. So the Picard iterates we had before were exactly this sequence, xn equals f of xn minus 1. One of the benefits of writing it this way is we see that Picard iterations are just a discrete dynamical system. It's perhaps a little strange, and it's a little subtle, because it's a discrete dynamical system, but the xn's are not numbers, real numbers, right? Each xn is actually a function. And so, unlike the discrete dynamical systems we talked about, this is a discrete dynamical system where the phase space x is the set of, C1 continuous differentiable functions. And in particular, it's actually something known as an infinite dimensional space. And so, yes, although in some sense it looks very much like what you've seen before, in another way, this is actually very different and very complicated, right? Because we're dealing with infinite dimensional spaces. Why is that infinite dimensional? That's a whole other story. Okay. But translating the Banach Fixed Point Theorem to another way, what we're really saying here is that there is a single fixed point. So there is a unique fixed point of our discrete dynamical system. So in other words, there's a unique solution to x infinity equals f of x infinity. And it, in fact, is a globally stable attractor. Right? No matter where I started, my iterates will always converge to this same function, x infinity. And so, yeah, it's all statements about stability, about fixed points. And so it's just a discrete dynamical system. And of course, again, one last time, translating this back to the integral form, why is this fixed point equation so useful? Well, the fixed point equation is saying that I have a solution to my integral equation, which is to say, a solution to my differential equation. And so that, I think, is like one of the coolest things about this theorem is we're taking this, this continuous dynamical system world, translating it somehow to this discrete dynamical system world in a very non-obvious and very, clever way. So this is just a small preview of sort of all the techniques that go into the actual proof. But hopefully you got something interesting from this. Hopefully at least piqued your interest to show that although we teach dynamical systems often as like there's the discrete side, there's the continuous side, in actuality, these are really intertwined and they talk to each other, these two worlds. And translating from one to the other can be extremely powerful. So if you have more questions, please come talk to me. I'd love to tell you more about the details of how this works. But this is a good place to leave it for now. All right, thank you.